When we talk about distributions and statistics, they can range from super simple to super complex. We're going to talk about a super simple one today, the continuous uniform distribution. And then we're going to talk about probably the one that you've heard the name of before at some point or some reference to it, because it's likely one of the most popular culture recognized distributions and statistics, and that's the normal distribution. Sometimes we talk about a bell curve. That's the normal distribution. So we're going to take a look at a couple of characteristics of these two distributions today, and we'll be working more with them in the future. The first distribution we're talking about is the continuous uniform distribution. So for the continuous uniform distribution, we have a density function for a continuous uniform random variable on an interval, a closed interval from a to b. And this density function is 1 over b minus a over that entire interval. So what this results in, if we graph this density function, is just a horizontal line between the value of a and b for our random variable. So if we imagine lines, vertical lines at a and b, then we can see that this is actually a rectangle. And thinking about continuous functions and the area underneath of continuous functions, we know that the area underneath of this horizontal line must in fact be 1, since we're dealing with a probability distribution. So if you ever forget what the density function is, you can just remember that the uniform distribution stays the same for all of the values between a and b. So it makes a rectangle, and the area of that rectangle has to be 1. So then you can figure out, you know that the base of your rectangle is b minus a. And so you can figure out that the height must in fact be 1 over that in order for the entire area to equal 1. Now, also, since it's the same value for all of the values between a and b, when we go to find the mean, we really are looking for the value exactly halfway between a and b. So to find that, we add a and b together and divide by 2. So finding the mean of the uniform distribution is also a very straightforward thing and easy to remember. The variance is a little bit more challenging, but not a ton. So to find the variance, we're going to take the difference between b and a, we're going to square it, and we're going to divide by 12. Our second distribution is the normal distribution. So the density of the normal distribution is a very much so more complex formula for us. So we find it by taking 1 divided by the square root of 2 times pi times the standard deviation of this normal random variable. And then we multiply that times e to the negative 1 divided by 2 times the variance of our normal random variable times the quantity x minus the mean of our normal random variable squared. So notice, once we know the standard deviation and variance, one or the other, and the mean of our normal random variable, then the distribution of our normal random variable is completely determined. So this distribution, while the density function is super complicated to write out, the picture that it creates is actually this bell-shaped function that never quite gets to the horizontal axis. It goes on and on forever towards infinity and negative infinity, never quite touching that horizontal axis. Its highest point above the axis, above the horizontal axis, occurs at the value that is the mean, and that highest point is called the mode. The curve is completely symmetric about a vertical axis that we can imagine being through the mean. It has points of inflection if we look 1 standard deviation away from the mean to the left and to the right of the mean, then we can see where its points of inflection are. It's concave downward if we're between the mean minus the one standard deviation and the mean plus one standard deviation, and everywhere else it's concave up. That horizontal axis, because we get really, really close to it without ever touching it, it acts as an asymptote for the curve. And this curve, despite going from negative infinity to infinity, the area under the curve is equal to 1. It is a probability distribution. Every probability distribution is set up that we can find the probability that a random variable is between two values by taking the integral from the first value to the second value. And so that area underneath of the curve is the probability. Now, the normal curve is no different from any other probability distribution this way. However, the normal distribution has a relatively complicated equation compared to some of the others that we've worked with so far. So taking that integral is maybe not something that we want to do on a regular basis. Luckily, we have a way to help us out. So we actually talk about a thing called the standard normal distribution to help us take that integral in a more helpful way. And in fact, we're going to end up bypassing taking that integral at all by making use of a table to find the probabilities that we need. So the table that I'm referring to is table A.3 in the appendix of your book. It's on page 735 and 736. And I'll be referring to that table as we work through a little bit. So we're going to talk about first how we can get from any normal distribution to the standard normal distribution, how we can use the table to help us find probabilities, and finally we're going to talk about how we could get from that standard normal distribution back to a normal distribution if we needed to do so. So here's the integral that we would need to take to find the probability that our normal random variable x was between the values x1 and x2. We would have a constant out front of 1 over the square root of 2 times pi times sigma, or our standard deviation, times the integral from x1 to x2 of e to the negative 1 divided by 2 times the variance, times the quantity x minus our mean squared, dx. So you'll notice my variable x is actually nested twice within functions, so it's really not a fun integral to take. But something that I can look at this and I can say, you know what would be amazing? If my standard deviation was 1, well, that would mean that my variance was also 1. And if my mean was 0, let's see how that changes this integral, just having those things be true. So what this will end up doing was we would have 1 over the square root of 2 times pi, because our standard deviation would be 1, times the integral. Now, we've changed. We're not actually in x's anymore. We're in some kind of new normal random variable where these things are true. So let's say our random variable is z, all right? So we're going to be going from z1 up to z2 of e to the negative 1 over 2 times the variance. Well, that's 2 times 1, so that's negative 1 over 2. And then my variable minus my mean, so z minus 0 squared. Well, that's just z squared dz. So this is actually an integral that's a whole lot easier to take and work with. So the question is, how do I get from x to z? Well, the answer to that is I take my z variable is going to be my x value minus the mean of my x value divided by the standard deviation of my x value, or my x variable. So anytime I'm looking for a z variable, I can just plug it in here. And what this does is it normalizes my mean to 0 and my standard deviation to 1 and gives me a value there. And in fact, when I do this, that z variable, normal random variable, the distribution of it is actually called a standard normal distribution. So any distribution of a normal random variable with mean 0 and variance 1 is going to be called a standard normal distribution. Now, even though this integral is much easier to take than the integral I had before, it still has a function nested within a function, so it's still not a fun integral to take. And we actually use normal distributions often enough that rather than have to take this integral over and over again, we actually have a table that gives us the values of this integral for different values. So in order to have a table, what we needed was to have this standard normal distribution so we can always have the mean being 0 and the variance being 1, so that all that we have to account for is our z values changing. So it's going to be very important for us to remember how to get from our x value to a z value so that we can make use of a table. So table A.3 on page 735 and 736 is going to be where we want to work. Now, the way this table works is every row represents a z value up to the 10th place, and then each column tags on 100th place for it. So if I wanted to find the area, the integral, for z value of, say, negative 1.83, I would go to the negative 1.8 row, and I would go over to the 0.03 column, and I would find 0.0336. And that gives me the area. Now, what area is that actually? It's an important thing. So in this table, the area that we're being given is always the area under the curve to the left of whatever my z value is that I choose. So if I want to find, say, the area to the right, all I need to do is do 1 minus the area that I'm given. And that's going to give me the remaining area underneath of the standard normal distribution. Now say I want to find the area between two values, z1 and z2. So the area that I want is this area right here between and underneath of the curve. Now if I read the chart, the area that it's giving me for z2 is really everything to the left of my z2 value. So it's all of that area. So basically what's happening is I don't want this area that's to the left of z1. So in order to find that total area, what I'm going to do is I'm going to be finding the probability that z is less than z2, so that gives me everything to the left of z2, and I'll subtract from that the probability that z is less than z1, which takes away all of this area over here that I don't want. So this is really taking the area to the left of z2 and subtracting the area to the left of z1. Now there may be times when I want to actually know what is the value of my random variable x. When I know the mean of the random variable x, and I know the standard deviation of the random variable x, and I want to know what value of that random variable x gives me a certain probability of my random variable being less than that value, say. Well, if I do that, I can go into the chart and I can find the probability that I'm looking for. So say I want a value of about 45%. So I want a probability So I'm looking for the x value, that like 45% of the values fall less than x. So if I go in my chart, I can find my value that's closest to 45. So if I do that, then I find a value of about negative 0.12 or negative 0.13. Either way, it's between those values. So what I do is I take the z value. So I'll take negative 0.13, and I know that equals x minus, say the mean that I'm dealing with is 40, and the standard deviation is 6. Now all I have to do is solve for x. So I'll have negative 0.13 times 6, multiplying both sides by 6, this gives me x minus 40. Adding 40 to both sides, I get negative 0.13 times 6 plus 40 equals my x value. And if I solve that, then I'll find that my x value is about 39.22. Now, we like to have things in general terms, so let's take a look at what solving for x looked like. It was really my z value times the standard deviation of x plus the mean of x gave me my x value. So whenever I want to go in reverse, I can use this formula right here, and I'll be able to get there. Now, you shouldn't feel like you have to memorize this, because we really can get there from one to the other very quickly and easily. So if you remember one of these, then you can manage to manufacture the other one very easily. So please don't feel like you have to memorize a bunch of things for all of this.